Now let's look at the normal probability distribution and what that is. This is where we will use tables and look up how to do things, as well as Excel. I'll do one of those later. So, as I mentioned before, this is your, the fundamental one that everybody uses concept. And you hear people say things like, well, it's normally distributed or it's normal, right? But what do they mean by that? And it has to do with how things are distributed. And so it's probability, it's chance, it's those concepts, but it doesn't always work like this. But this is what most things like occur. Like for huge samples, like if you were to take the population of the world, which is in this 7 billions by now, and you looked at the height of everyone, would be normally distributed. There's just no question. It's not skewed one way or the other. There's going to be a mean in the middle, and then there's going to be, so actually let's start talking about it. So this is mu for the population, is always in the middle of that. And the percentage of the population would be this distribution. It'd have that bell. We call this the bell curve, right? So it's the bell, like an upside down bell. So all of those is, when we talk about that, is this normal distribution or is distributed normally? That's how you say it. So the function, I'm going to show you this, what it looks like. So the function that creates this thing, so this is your f of x, okay, and that approaches positive and negative infinity. It looks like this. So f of x is equal to, now remember sigma and a bunch of other symbols, is 1 over, this is your coefficient, sigma times the square root of 2 pi. How someone derived this, I'm not sure. And then it's the number e raised to the, and this is a fraction. I'll try to draw it like a fraction. This is the exponent. It is negative x minus mu, that quantity squared, divided by 2 sigma squared. So those are parameters. Your mu, which is the average or mean, and your standard deviation is sigma, another one here. And then this derivation, that comes out in the derivation of this function, this distribution function. This is a power to e. So it's basically behaving like, I'll just say h of x is a e to the negative x squared. And that function is essentially that upside down curve like that. So we're interested in the area under that curve. So this function is the probability function. You have x in the range or domain is negative infinity to infinity, although obviously you never approach infinity, right? And I copy this curve over. It's really hard to draw it perfectly symmetric, but that's what it looks like. And then these are the number of standard deviations away from the mean. So you'd be able to say that the first one here is mu plus sigma. This is mu plus 2 sigma. And then going back, this is mu minus sigma. And this is mu minus 2 sigma. And then you could go further and go to another standard, 3 standard deviations from the mean. And so we might be interested in what's the probability that someone will score on a driving test between 5 and 8, whatever that may be. And you would know the information, and then you calculate this area. Well, you don't actually use that function. That's just sort of like an FYI. You would never even come across that unless you studied statistics itself. We just use computers and packages to calculate those. So just as above for the probability density function, the area under that curve is 1. So a couple things about this. This is symmetric about sigma. I'm sorry, mu about the mean. The area under curve is 1. So what that would imply then is that this area here is equal to 0.5, and this area over here, everything else on the right side, is also equal to 0.5. Okay, so it has to be, right? Because it's symmetric, and that's the middle, right? And then each side has to be half. Okay. Those rules that we talked about, empirical rules, occur. So between the two standard deviations, so just take height of the world or something, people of the world, then everyone is between 68% of the population is between those two means. And if you go out to another, you're over here. Okay, so, and that was the, what was it, 68, and then I forget the numbers. But those are how you can, it's the same concept we had talked about before, but this is how the curve looks, and this is the continuous random variable. Okay, let's move this up a little bit. This is how the curve will change. So this is for different sigmas. So your mean is the middle, and then that's a fixed value, whatever the population mean is. And then different sigmas will make it basically flatten out and go way out here. That is a smaller sigma, or I'm sorry, a larger sigma will make it go like that. Let me get rid of that. And then a real small sigma will make it crunch up. So this would be a small sigma, make a real crunch. Well, that's how it works. Like, there's not as much data on either side, or information, stats on either side of the mean. It doesn't deviate very far. So depending on the sigma, you're going to get that different curve. You're going to get a real steep one, or you're going to get a real flat one. So a more flat curve has a large sigma. A small sigma goes really high. Remember that the area always has to be 1. Okay, the next stuff to look at is basically how to calculate the probabilities. So we use the standard normal random variable. So we use the standard normal. So let's see, did I have that written down? I'll write it now. Okay, so the standard normal random variable and it's basically standardizing whatever x is. So if x is height or something, just stick with that, then we don't want to be talking about meters or feet or whatever. We want to talk about the same value. So you take the units off and you just call it, what's the mean? That's 0, and then you're on either side of 0. It's positive or negative. So the mean becomes 0. So we use the z-score, z equal to x minus mu over sigma. Okay, or we can say we solve for x, that's mu plus z times sigma. All right, so what happens is if x is less than, a couple things here just to go over, x less than mu, then z is less than 0. And vice versa, x greater than or equal to mu, then z is greater than or equal to 0. So remember that basically what this does is put the mean at 0. And then you're talking about the same standard deviations from that 0 point. Okay, so we are interested in those probabilities. Let me go back to that graph. Let's do another one. So we are interested in see, I knew I couldn't draw that very well. Let's just add one. Let's add the stickers. I just added one in here. Oh, there it is. And then you can't see it. So what I have to do is I have to convert to ink. And then I have to highlight that. Click on it, go to style, and make that into a chart. Okay, so there we go. Kind of wish these weren't here, so I'm going to erase them. So those are supposed to represent the standard deviations from the mean, but I don't want them there because I want to talk about this. I want to say, all right, so we're interested in what's the probability that your x is below this value. Okay, so what's the probability? Well, that's basically finding this area under the curve. And it goes off like that. So what's this area? Well, technically to do that, you need some mathematics to do that. You can't, that's not a simple function. Remember that curve is that function I just wrote above. So what's that area? Well, we have tables for that. That's what we use. So these tables are tabulated from left to right. They basically add up the area from left to right. So when you look up this number, it's this area. So let me show you the table. I have it right down here. Okay, these are the tables we're going to work with. And see, that's the area. So it gives you the z value here, and then it gives you this sum. Well, that means if we want to find, let's say, this area, let's duplicate. So now suppose I have this, and let me change this up just a little bit. All right, so I don't want that, I don't want that. What if I want to find the area between these values? From here, we'll say A, and we'll make this a B, and now I want to find this area, or meaning the probability that the height of people or the number of car accidents or whatever, the number of something is between A and B. So this probability, I gotta change the color on that sucker. Okay, so this probability is x less than x naught. And remember, it doesn't matter whether you put equal to or not, because a single point doesn't give you area. This probability in question would be between those values. Okay, so that area is the probability that x is between A and B. That's how you'd write it. And so what you do, and I'm going to show you the numbers here in a second, is you look up the table and you find this total area, like that, and then you subtract off whatever that says. So what this actually equals then, this is 4 tabulated z-score. So accumulation tabulated z-score. It's the you do the probability of z less than b minus the probability of z less than a, because that's what it gives you when you do the calculation. Okay, so then I'm gonna. It only works for this. Only is true for the tabulated stuff. You add it up. So let's do an example on one, and let's see. So let's just do it here. So find the probability that z is less than, and I picked a couple examples. They go through that, how to do that, but I'm just going right to the examples. So probability that z is less than 0.9, 0. Then what you do is you go to the tables, and that's z, so that's a z-score. It's standardized. And I actually already highlighted it, so pretend I didn't. So you find 0.9. Here it is. And it's I didn't mean to erase it. It's 0.90. So the decimal is up here. So it goes to basically 2 decimals. So it's 0.90, 0.91, 0.92, 0.93, etc. All right. So you go to 0.90, and that's the sum of the probabilities from negative infinity to 0.9. That's exactly what this means. Right, so this means basically x is between, I won't say equal to. This means x is from negative infinity, not x, z. To 0.9. So it's the sum. Sum of the probabilities. That's how it works. That's how those tables work. And so that answer, you just say equals, and whatever that was. I had it highlighted on purpose for a reason. It was this one. 0.8159. And then put all those numbers down. 0.8159. So that's looking at, so it's like this case up here. You're looking at all that sum right there, all of that. Okay, let's do another one. Okay, so I'll do another example here. And I'm just picking some random ones in here. So probability 0.58 less than z less than 1.74. So that's everything between z between 0.58 and 1.74. So you're going to find the probability that z is less than 1.74, and then you're going to subtract the probability that z is less than 0.58. And that, again, only works for the cumulative tables. That's not like true statement. So the cumulative tables is what you're looking up there. and then you subtract them. So let's go to 1.74. So 1.7, and then this is 0, 1, 2, 3, 4. So 0.9591, 0.9591. So 0.9591. And then we're going to subtract, oops, put the wrong spot, 0.9591 minus, and then we got to look up the 0.58. So the 0.58, it's right here. So 0.5, 0, 1, 2, 3, 4, 5, 6, 7, 8. 0.7190. 0.7190. 0.7190. And then you subtract those. So we get our calculators out. I don't see my 4-function calculator around here. I use this one on my little iPad. Where is it? Okay, so you got 0.9591 and then 0.7190. And we subtract. So that probability is 0.2401. That's how you do it. That's how you use these tables. You gotta be able to use those tables. There's other ways of doing that on computers and other packages, but this is what we rely on most of the time.